For example, the pen in your hand is moving from right to left, but in fact there's a theory that it isn't moving. In short, if you compare it to water, you drop something in with a plop, right? You get ripples, right? The ripples move, but the water molecules aren't moving, right? It's undulating and moving, but the ones there are only moving up and down. But to the eye, the waves move outward, but the antibiotics that are there aren't moving. Perhaps the antibiotics we can know, atoms or protons and neutrons, and further below there should be antibiotics that make us up. Those constituents are actually spread throughout the entire universe, and there's a possibility they aren't moving. Otherwise, things like gravity can't be explained. The world of speed. A permanent keeper. So this time I'm thinking of targeting all sorts of things. I want to explain their speeds and the mechanisms. It's not a perfect ranking, but in a sort of gradually faster order, I'd like to introduce speeds. Usually it'd be like, no. 1 exclamation mark light. That's not interesting, right? Like, we know that. Since that's not fun, a speed ranking including sci-fi. Of course warp drive comes in. First up, E. coli. The speed of E. coli converted to per hour is 12.6 millimeters. Moving a bit over 1 centimeter in 1 hour is E. coli. Pretty slow, isn't it? Slower than I thought. It gains thrust by the rotation of flagella. The motor that spins this whip does 2,000 revolutions per minute. It even has a clutch apparently. Its structure is very close to an artificial motor. It has many commonalities. Looking into it, it seems the motor is rotated using ions. What's interesting is they artificially modified E. coli so that both sodium ions and hydrogen ions can be used. They made a hybrid E. coli which skillfully uses sodium ions when sodium ions are abundant and skillfully uses hydrogen ions when hydrogen ions are abundant, switching as it propels itself. There are residues called charged amino acids, and apparently they have electrostatic interactions. No doubt it's turning by electrical power. Next, suddenly a human, Usain Bolt, 45 kilometers per hour. That's the record when Bolt ran 100 meters in 9 seconds and 58 hundredths. There's also a record for a human running on all fours.
Huh?
How fast do you think the record when a human runs on all fours is? 100 meters.
Isn't it slower than Bolt?
Amazingly, it's slower than Bolt. But 17 seconds for 100 meters? Think about it. Can you run on all fours? 17 seconds is the average record speed for adult women in the 100-meter dash. There's a person named Kenichi Ito, and he's in Guinness. He keeps breaking the top record for all fours running. He's never lost. Gallop running, basically like a horse, a style where you bring both legs forward. It means it's the same running style as other quadrupeds, and he does it this way. He himself says, eventually it will surpass bipedal running. You laughed, didn't you? It's true. In short, we're not used to running on all fours, and if you train, all fours is definitely faster, is his claim. In terms of build, there are people with very long arms, right? If people like that trained, there might be a chance. Okay, next. A horse, 90 kilometers per hour. A thoroughbred's top speed is about 70 kilometers per hour. Huh? So thoroughbreds aren't the fastest. Thoroughbreds have been bred to be faster, right? Even so, 70 kilometers. I looked into this. In reality, the speed at which they can set records in horse racing is 70 kilometers. In short, as speed increases, endurance probably drops. So for thoroughbreds, 70 kilometers per hour is probably best. In fact, the horse that does 90 kilometers per hour is a riding horse called a quarter horse. Apparently they're a bit smaller in build. This one reaches 90 kilometers. There are types of quadrupedal locomotion, and if you watch a horse, only the legs are moving. You see the same thing in Abarenbo Shogun, right? Horses run as quadrupeds, using only the parts below the hip/shoulder joints. That's how horses run. It's ecological. It saves energy. They can run by moving only part of the body without moving the whole. Therefore, high-speed travel is possible with minimal exertion. By the way, have you ever wondered why horses have hooves? They're running on a nail and on a single toe.
I don't know.
We humans have 5. Cats also have 5. Pigs have about 3. Cows have 2 as well. Horses have 1. In evolution, this went from 5 to 3. and ultimately became only the one corresponding to the middle finger. And this is, when accompanied by rapid acceleration, probably to reduce the load, isn't it? In short, with the toes all separate, it's complicated, right? Because they do rapid acceleration and long distance movement outdoors. Moreover, to keep running endlessly at 70 and 90 kilometers per hour, soft toes aren't suited. Because they run on hard hooves, they can withstand strong output. So in the end, didn't they evolve to a single toe, is what people say. If humans ran at 70 kilometers per hour, the soles of their feet would be shredded for sure.
Will humans also end up running only on their big toes?
No, humans won't evolve to run only on the big toe. There's no need. Humans don't need to run away from anything. Still, it's strange, isn't it? It's a nail. It's epidermis, a nail is. In that sense, I think horses have undergone interesting evolution. Next, the cheetah, 120 kilometers per hour. That's famous, right? I think it might actually be even faster, because in fact, the cheetah has a record of running 700 meters in 22.4 seconds. Isn't that incredible? 22 seconds is a human 200-meter dash. From that, they calculate the speed, and 112.5 kilometers is what you often see written. So, I think the top speed is even faster. It's said they accelerate to 72 kilometers in 2 seconds to reach top speed. So the actual top speed exceeds 120 kilometers. Unlike horses, cheetahs don't have hooves, so they can't run for long. If they tried, even a cheetah's legs would get shredded. A cheetah's claws, being in the cat family, are sharp and attached. But unlike a house cat, they can't extend and retract them. They're always out. Those are said to function like spikes. Even in track and field, wearing spikes makes you over 1 second faster. It's a huge difference. Also, unlike the horse earlier, they use the motion of the spine when running, which enables high-speed movement. Someone calculated the energy during a cheetah's acceleration, and if Bolt is 1, a cheetah is 4 in terms of output generated during acceleration. Otherwise, you wouldn't hit 70 kilometers in 2 seconds. Next, dolphins, 65 kilometers per hour. Doesn't it make you wonder, why can they swim that fast underwater? Don't you think there must be some secret? We found out something astounding.
What is it?
I'll talk about that in a bit. First, dolphins. They move the whole body up and down, flexing. That's how they get thrust. You know I like robots. It makes me want to build a fish swimming robot. I daydream about all kinds of things. But even if you move the body sideways, it probably won't go forward. That's easy to imagine, like, that thing doesn't move forward at all. Anyway, the robot just doesn't work well. That's because thrust acts in both directions. From the side, dolphins flex their bodies up and down. This is apparently about angle of attack, and with that motion thrust acts in one direction. To get complicated, there's center of gravity and aspect ratio and such, like which axis of motion is efficient and so on. And with that kind of angle of attack, fish and dolphins move forward. Especially for dolphins, the flukes even have muscle in them, unlike fish. There's also research suggesting they relax when lifting the tail and tense up when stroking, stiffening it. That way they obtain thrust very efficiently. That's one possibility. So how much resistance does water have? The density of water is 800 times that of air. Anyone who's swum knows its tremendous resistance. If anything, swimming without goggles makes your eyes hurt, right? But if you just open them underwater, it doesn't hurt.
It hurts.
Really?
Maybe my eyes are weak.
Is this turning into some other kind of consultation? Anyway, the water pressure makes it hurt. For example, on a motorcycle without a shield, once you exceed 60 kilometers per hour, your eyes hurt.
I thought my eyes just hurt because they were dry.
That might be part of it too. In any case, dry eyes also hurt because of friction with the air. To actually propel yourself at 50 kilometers underwater, you'd need 7 times the muscular strength a dolphin has. There's research saying a dolphin's muscular strength is far too insufficient. Where does this gap come from? It's probably largely due to dolphin skin. The skin seems to be made of something like a hydrogel, absorbing moisture, and apparently it's squishy. That may be working effectively, and dolphin skin reportedly peels away bit by bit every 2 hours. With a skin cycle like that, The flaking skin might be the reason they minimize water resistance. Among marine creatures, even faster is the sailfish. 110 kilometers per hour. 110 kilometers. There's one even faster. Striped marlin, 130 kilometers per hour. At that point, even the eyeballs surely couldn't take it.
If it's like this,
I feel like they definitely pop out. So I looked into various things. You know the water jets from a fire truck, the water blasting out. Apparently that's 400 kilopascals. 1 Pascal is apparently the force of 1 Newton per 1 square meter. And 1 Newton, when converted per 1 square meter, is apparently 102 grams. So it's like carrying and lifting 40 kilograms worth of resistance, constantly. Those water jets, about 10 meters per second, right?
looks painful, right? People get blown away by it.
Yeah. 10 meters per second is 36 kilometers per hour. If you swam underwater at 36 kilometers per hour, it would be like taking a fire truck's water jet head-on. Starting to get it?
I'm starting to get it.
Starting to see how your eyes would gradually get wrecked.
If you get blasted by a fire hose, you're done. That's a weapon, right?
A weapon. Even with these glasses, who knows what would happen?
It's not at the level of glasses.
Anyway, at 36 kilometers per hour, this is the force. Can you believe it? A typical submarine is 20 knots. That's 37 kilometers per hour. And a nuclear submarine, a powerful one, right? 30 knots, 56 kilometers per hour, about the same as a dolphin. A nuclear submarine. In short, it's a screw propeller. I think the screw is an enormous invention. It generates considerable thrust. And even then, you only get this. How many secrets are there really?
Right.
That said, research on these marine creatures actually hasn't progressed at all. But field guides write things like 100-something kilometers. Recently, we've been able to attach sensors to marine animals and measure them. Then we learned their speeds. This wasn't dolphins, it was marlin, 18 kilometers.
Huh?
The measured value was 18 kilometers per hour. Apparently that figure comes from someone measuring how much the reel got pulled when one was caught. It's written in encyclopedias. Scholars also say the source is unknown. Why is that speed written there? It's really an urban legend.
Wasn't the ship just moving at high speed?
It was just the marlin being pulled. So, you have to wonder, right? When measured by GPS, the top speed was 18 kilometers per hour. There might be slightly faster, momentary bursts though.
Even so, it's totally different.
It's completely different.
It's about 10 times different.
After hearing all this so far, you kind of get it, right? The pressure from the water jet and that eye pain. In short, water pressure isn't that forgiving. Even at 18 kilometers per hour, the water pressure is tremendous. A propeller-driven submarine only does 37 kilometers after all. So, 130 kilometers per hour turns out to have been an urban legend. By the way, I looked up the world's fastest boat. This one has 1,550 horsepower. Its world record speed is 290 kilometers. That's fast. It pretty much looks like it's flying over the surface, skimming, bouncing as it goes. Okay, next. Let's go to the sky. There wasn't much for the sky, so the fastest one, the Peregrine Falcon. That's pretty offhand. A Peregrine Falcon's speed is 390 kilometers per hour. In normal level flight, it's around 100 kilometers. When it spots prey and goes into a dive, it's said to have actually reached 386 kilometers because it folds its wings and drops at high speed. That's how its eyes can withstand it, since it has a nictitating membrane and so on. Anyway, whether it's being able to withstand pressure or having great spatial awareness, they've got the necessary abilities, various ones. Among animals, some are fast and some are slow. Horses, cheetahs, you name it. I think there are actually even faster ones. In the animal kingdom, we haven't measured speed itself precisely, so there may be differences. With training, they can get faster and stronger. For humans, if you actually take the average, a typical high schooler runs 100 meters in about 14 seconds. Women are about 17 seconds. Compared with Bolt, that's a 30% gap. I don't think animals show that much spread. Everyone out there works hard to survive, whereas humans take it easy, so gaps are more likely. Animals get faster and stronger when trained. Racehorses get faster with training, and Tosa dogs get stronger with training. Humans are incredible. We can train ourselves. That's it for animals. Next up, cars. Not the very fastest, just a fairly fast one. Bugatti Veyron, a car that costs 300 million yen, a so-called supercar, 1,500 horsepower. It's insanely powerful, which is what makes it fun. The engine is what's called a W-type 16-cylinder. You know V-type, right? The cylinders arranged like the letter V in English. This has two of those, forming a W. It's a special engine as well. 16 cylinders, turbocharger. Displacement is 8,000 cubic centimeters, with a maximum torque of 163.2 kilograms. For a regular car, the torque is usually around 10-something kilograms, right? Even for a sports car, having 40 kilograms of torque is considered pretty impressive. Torque means how many kilos you can put on the end of a 1-meter bar to turn it, that kind of thing. It has enough force to suddenly spin something with 163 kilograms attached 1 meter out. That's more than double a heavy trailer. As for this Veyron, the engine is so ferocious that the cooling is incredible too. It carries 50 liters of coolant and needs 23 liters of engine oil. The car is 4-wheel drive. At launch, it uses all 4 wheels, but in the end, the front wheels bear almost no load, only the rears are driven. It feels like a computer is doing the driving. From a standing start to 100 meters takes 2.5 seconds, to 200 kilometers takes 7.5 seconds. As speed increases, it takes longer and longer to reach it, and it takes 16.7 seconds to reach 300 kilometers per hour. To hit 431 kilometers at top speed, you need 11.5 kilometers of straight line distance. Next, the thrust SSC, 1,227 kilometers per hour, Mach. This was on October 15th, 1997, in the US state of Nevada, achieving 1,227.985 kilometers per hour. This is the fastest for an automobile.
Isn't this a plane?
No, this is a car. It has tires. Overall length 16.5 meters, width 3.7 meters, weight 10.5 tons, mostly engine volume. In fact, it uses the same fighter jet engine as the British spec F4 Phantom, the F4K. Total thrust 223 kilonewtons, consuming 18.2 liters of fuel per second. 18.2 liters per second. Way worse fuel economy than something like a jumbo jet. Converted into more common units, at top speed, the fuel economy while running is about 80 meters per liter of fuel, meaning 80 meters on 1 liter. The first car in human history to break the sound barrier. Next, trains, the TGV. Back then the Shinkansen was around 200 kilometers. Even though in the Shinkansen song they make you sing 250 kilometers per hour, I knew it. It didn't hit 250 kilometers. At that time, the TGV exceeded 300 kilometers. I was like, the TGV is amazing. Japan's losing.
That's spin.
Well, that's not really the point. This is a train operated by the French National Railway, and I think this was a record set in testing. I saw the footage too. It's amazing. Unlike Japan, it's real countryside, nothing around the tracks, pretty much straight, and it tears along at incredible speed. And the dust all around is incredible. It races along kicking up clouds of dust. It's like, that's not a train. Japan's Shinkansen is much sleeker, right? It always runs on elevated tracks. The TGV uses ordinary track, with ballast laid down.
And that's dangerous.
Dangerous, dangerous. Maybe it's different now though. And speaking of the TGV, it's a locomotive hauled system. The front unit has the power, and the rest are just unpowered cars. That runs at incredible speed, but with Japan's Shinkansen, every car has power. Every car has 2 motors. It's built completely differently. I looked into this a long time ago, and wondered why Japan doesn't use locomotives. Because of differences in steel materials, the rails deform more easily. With a locomotive, that one point takes the load, the pressure piles on. If you watch that footage, you know pantographs, right? The things mounted on top of the cars. At high speed, they hit the same spot and only that spot breaks off. So on the Shinkansen, the overhead line is strung in a zigzag. From the train's perspective, it's designed to move evenly and in balance. It's set up that way to prevent only one spot from wearing down. And one more thing, a train's pantograph. It draws power, right? I used to think it drew from the front and returned out the back, the electricity. But actually, it draws from above and returns it to the rails. They've really thought it through. So, if you're holding the strap and don't touch the rails, you won't get shocked. To go any faster than this, you need more output. And you overcome the friction between wheels and rails, so they start slipping. So you probably can't go much faster than this. I think it's already slipping a lot at this point.
Basically, the top speed of trains.
Around 600 kilometers is probably the limit. Next, something said to exceed that limit. The maglev. Japan's maglev. This one is 603 kilometers. Fast, right?
Doesn't vary that much.
Aren't they not even trying? Theoretically, if they wanted, it should go even faster. All you have to do is change the switching speed. There's probably no point in going beyond this. The operating speed is set at 500 kilometers, so if it hits 600 kilometers, there's no safety issue, and it runs stably. This one does 600 kilometers. This one, with the TGV, when it's doing 500 kilometers, everyone's bodies are shaking all over, kicking up dust. Totally different, so composed. This is a levitating type train. Japan's version kind of hangs by the power of superconducting magnets. It's not exactly floating, it's hanging by the hairpin effect. It runs by a mechanism of magnetic switching. Its nose is even longer than the Shinkansen's. When it exits a tunnel, it makes an incredible sound, like a boom, a bursting sound. This is what they came up with to deal with that. It's like the lead car is almost all nose, right? Okay, next, Hyperloop. 1,287 kilometers per hour. That's Mach 2, basically a tube train. What they call Hyperloop is the one Tesla Motors talks about. This also reduces the pressure inside the tube. In short, you reduce the air to eliminate air resistance. Eliminating it completely would be costly, so they just thin it out. And the maglev runs through there. A capsule driven by electromagnetic force, seating 28, achieving ultra-high-speed travel, more than twice as fast as a maglev. Something like that. Next, bullets. A 15.2mm Steyr APF SDS. That's what it's called. An unbelievably large round you couldn't even hold. Its speed is incredibly 5,220 kilometers per hour. That's around Mach 4, isn't it? An amazing speed. It's a rifle, but I just want you to realize bullets are that fast. Okay, next. Fighter jets. The fastest fighter is the MiG-25, built around 1970. 3,392 kilometers per hour, Mach 3.2. They say this still hasn't been broken.
I see.
It's pretty big, a large fighter with a maximum takeoff weight over 40 tons. By the way, the latest F-35A, that single-seater, has a maximum speed of Mach 1.6. The F-22 is around Mach 2. Apparently, any faster than that and the body melts from heat. Rather than frictional heating with air, it generates tremendous heat from compression heating. It's called the heat barrier. Okay, next, the X-43A, 12,144 kilometers per hour, about Mach 10. This one was developed by NASA. It's unmanned. It flies with a scramjet engine. So it's an airplane, not a rocket engine. The marvel is that it's not rocket propelled. What that means is, it doesn't need air. Put simply, rockets carry hydrogen and oxygen, combine them, explode them, and use that thrust. There are solid fuel ones too, but that's the basic idea. But with a typical airplane, a jet engine, a turbojet burns fuel, spins a turbine, spins a propeller, and flies. And this one isn't rocket propelled. In fact, it does carry hydrogen inside. But since it takes in air from outside, ignites it, and uses it for thrust, it's kind of a half rocket. The point is, it doesn't need to carry oxygen as propellant, so apparently it only carries about 1 kilogram of fuel, though 1 kilogram of hydrogen is quite a lot. As of now, within the category of airplanes, this is the fastest. Okay, next, missiles. It's the R-37, 6,360 kilometers per hour, Mach 6. A Russian air-to-air missile, solid fueled and fairly big. Overall length 4 meters, weight 600 kilograms. Among missiles, this seems to be the fastest for now. Next, a ballistic missile on a lofted trajectory. In other words, a trajectory that goes up high and then falls back down. This is 18,000 kilometers per hour. Converted to Mach, it's 16.9. Fast. Next, Tomahawk. This is 880 kilometers per hour. A bit slow. This would be an unmanned winged aircraft, right? That's what's called a cruise missile, and it has an imaging type guidance system. It has a camera, and it can check its position as it flies. It flies fast at low altitude. It can do that. So in short, it's an unmanned airplane. It's called a cruise missile. As for weight, 1.2 tons. Overall length, 5 meters 56 centimeters. Not insanely large, right? It's powered by a turbofan engine, the same kind used on aircraft. A jet engine. So it can keep flying for quite a long time. Long distance travel becomes possible. Its range is 3,000 kilometers, so it goes a fair distance. This is apparently called a spear that's too long. Basically, as in there's no need for it to fly this long. In short, there are missiles for striking warships, and there was talk of using this for that, it seems. But it's too capable for that. Its uses are somewhat limited. The Tomahawk. Maybe it doesn't actually need to be fast. For a cruise missile, I mean. If it can fly slowly while staying hidden and strike all of a sudden, that's fine, right? That's what I think. But apparently they did consider a fast one at the time. That was the Smart Tomahawk at 4,240 kilometers per hour. Mach 4. It was actually cancelled. They decided it was pointless. Okay, next. Kinzhal. A Russian missile. 10,600 kilometers per hour. Mach 10. According to Putin, an invincible missile. When this missile is launched, it rapidly speeds up to Mach 4. Then it first climbs to an altitude of 500 kilometers, and from there uses its falling speed to reach up to Mach 10. Overall length, 7 meters 93 centimeters. Weight, 4.3 tons. With a range of 1,500 to 2,000 kilometers. Maybe this is the fastest one among missiles. Next, railguns. There are various kinds, so I'll go with a representative type. 28,800 kilometers per hour, converted to Mach, that's 27. It's called electromagnetic launch, or an electromagnetic acceleration gun. This is one that accelerates using magnetic force. It uses a device that accelerates objects via electromagnetic induction. It's the magnet-based one that fires rounds with this. And then there's what's called a thermal gun, which, instead of electromagnetic induction, uses the joule heat of the input current to turn the conductor behind it into plasma, and then expels it by pressure. A railgun has the feature of being extremely long. The longer it is, the higher the speed in theory. If you push the speed beyond this, the projectile itself evaporates. Next, particle beams. Sub-relativistic. We're talking like 99.999% of light speed. This is a device that fires charged particles, protons, electrons, heavy ions, and so on. It's kind of got one foot in sci-fi. You bend them with magnetic force, right? But they're affected by Earth's geomagnetism and such. So basically, it's an unusable weapon. On the ground, it's 100% unusable. Because if sub-relativistic particles fly through air, it would probably be a disaster right then and there. I think it's something that could probably only be used in space. Also, there are concepts using antimatter, anti-hydrogen, I suppose. If you were to fire antimatter, the moment it hit the target, the antimatter and matter would combine and annihilate. It disappears from this world. At the same time, 100% of the energy contained in that matter would be converted, causing an enormous explosion. This too obviously can't be used on the ground. It would be a space-only weapon. Next, Earth. The speed at which Earth orbits the Sun. How fast is that? 108,000 kilometers, Mach 100. Okay, next, a star. There's one in the Milky Way called US 708. It's moving at an incredible speed. This is the fastest celestial object currently observed. In kilometers per hour, that's 4,200,000, Mach 3,962. This apparently casts a bit of doubt on the existence of dark energy. It's odd for something to move that fast. Even though dark energy is supposed to be pulling, the fact that this thing moves leads to talk like, isn't dark energy a bit weird? That's the kind of discussion going on. Next, Apollo 10. This is 39,897 kilometers, Mach 37.6. This was the speed on return to Earth. Next, Voyager. 55,347 kilometers per hour, which is Mach 52. This was launched in 1977. As of 2013, it was about 200 million kilometers from the Sun. It seems they did an engine startup test in 2007. Apparently it still works. We talked about how it was finally about to leave the solar system or not, right? Go Voyager. Next, the Parker Solar Probe. This is a solar observation probe, and its speed is the fastest of any human-made object. It's 692,000 kilometers per hour, Mach 652. It's whipping around near the Sun and Earth over and over. It'll hit its top speed soon, won't it? Not sure though. Next, nuclear engines. There's something called Project Orion. If something like a pulsar came into the solar system, there might be times we'd have to leave the solar system. When leaving, if we say, let's go to Proxima Centauri, the nearest star, it's 5 to 6 light years, so it takes time, right? So, thinking what kind of engine could work, they came up with this nuclear engine. Using fission energy or fusion energy, you blast propellant out and move forward. You reach a speed of 1/30 the speed of light. This is called an Orion-type interstellar spacecraft, and it would take 140 years to reach Alpha Centauri. Okay, next, antimatter engines. These are sci-fi for now. That's because we don't have the technology to hold and store antimatter yet. 100% not. So it's thought this could reach 40% of light speed. With antimatter, you eject energy forward and backward. Then that mass becomes your propellant. It goes out the back as propellant and also out the front. You catch it with something like a vane and double it. That's the idea, apparently. With this, to Alpha Centauri, you could get there in about 10 years. That's a speed of 40% of light. At that speed, the twin paradox effect would be pretty extreme. Moving on, warp drive. This is Star Trek's warp drive. It's a technology that creates subspace and travels through it. This subspace is a hypothetical space for now, but in it, the mass of matter can be made smaller than in reality. That's the rule. It's different from the space we inhabit. In our space, the closer you get to light speed, your mass becomes infinitely large, and so on, so you shift to a completely different space to travel. That's warp drive. In Star Trek, for warp speed, they use the term warp factor, or warp coefficient. This warp coefficient is counted by the number of warp fields the starship projects. The speed increases by powers of 3/10, so the speed grows by that calculation. So the speed of warp 10 is not 10 times warp 1. In Star Trek's setting, you can only project up to 9 warp fields at once, but there's also warp 10, the so-called top speed, infinite speed. That represents being everywhere simultaneously, an infinite speed. You generate this warp field and accelerate within it. Warp 1 is the same as the speed of light. Warp 5 is 214 times light speed, and warp 9.9999 is the highest speed achieved by humans, at 199,516 times the speed of light.
Hold on, are we talking sci-fi?
Yeah, I know.
When you say humanity achieved that, do you mean Star Trek?
Right, Star Trek stuff.
I wondered what you were talking about.
This warp drive is a type of warp travel that moves through space at hundreds of times light speed, and this warp travel runs on a warp drive, which in 2063 in the state of Montana, USA, was developed by Dr. Zephram Cochrane. That's the setting. Next, transwarp drive. In the warp drive world, Star Trek's warp is famously slow. From one end of the Milky Way to the other, takes 100,000 light years at light speed. There's Star Trek Voyager, and people said it would take 70 years to get back. Warp is that slow, so it shows how slow light speed is. As the name suggests, transwarp implements warp by a completely different mechanism to exceed it. There are various kinds. Parallel universe warp, a mycelium network. There are things like cosmic fungi. Their spores are all over the universe, forming a network there. They developed a way to use that to reach any place in seconds. It's a bit shaky, this warp method, kind of relying on others, not something done solely with human technology. Next is wormhole type warp. You know wormholes, right? With supergravity, space gets warped there and connects to other regions. This one can cross the galaxy in tens of seconds. There's what's called the Borg Collective, a kind of robotic life form. And within the Milky Way, the Borg Collective has built a network of these wormholes. So the Borg Collective can jump anywhere instantly with this. Lastly, the fastest within transwarp, the quantum slipstream drive. This one's wild. Absolute speed, warp 10. Simply put, you create a warp field in front of yourself while sending out another probe-like craft. Using that, you raise your speed in a slipstream condition. This is developed in Star Trek, Voyager, and it keeps surpassing that warp, 9.9999, until the people aboard end up existing everywhere in the universe. That's what infinite speed means.
Speed is defined as moving from one point to another. That's the kind of definition it has, but
That's right.
if these exist simultaneously, I feel like that stops being the definition of speed.
Distance zero.
If the distance is 0, doesn't that mean it didn't move?
In short, once you reach top speed, the time to travel becomes all zero. Then you end up existing in the same place simultaneously. The speed becomes infinite. It's the same as everything becoming zero when multiplied by zero. A situation where you exist at all places at the same time. But he came back. He came back messed up, saying things like, I saw everything, I saw all of the universe. That's the quantum slipstream drive.
Does this mean objectively that there are many of that person?
That's how it is.
When you say everywhere, Yusan is also at a spot shifted by 1 millimeter, right? So it's all Yusan then.
The entire universe, Yusan.
That's what it means, right?
The Q continuum.
What is this? Is it a vehicle?
A life form. It appears in Star Trek. Not only can it exist anywhere simultaneously, it can exist anywhere in time as well. Various Qs appear, but they're all Q. Anyway, it's omniscient and omnipotent, but it's not that quick-witted. Makes you wonder if omniscient and omnipotent is the right term, so it came to humans for ideas. Anyway, this is probably the fastest thing in existence. Warp is actually being researched, even by NASA and such. There are a few actual theories, but they require tremendous power. So it's difficult right now, though it might become possible. Related to that is, nothing outruns light. We can't move faster than the matter we're made of. So surpassing light speed is fundamentally very hard, I think, overturning that theory. But there's cosmic expansion. The expansion of the universe exceeds the speed of light. As a relative speed, you can't exceed it. So I think it's not actually exceeding it. And there's the idea that space itself is expanding. So whether you can add that to speed or not, there are discussions like that. Then it turns into the question of what speed is. So arguments about exceeding light speed are actually quite difficult for now. As for the edge of the universe, I think the Big Bang happened 137 or 138 million years ago. And of course we can't see earlier than that. They say the universe is expanding and accelerating, but in reality, this keeps getting overturned. And there are even claims like actually it wasn't accelerating. It's odd. If it exploded in the Big Bang, it should be uniform speed, right? Same inertial frame, continuing to accelerate forever. Doesn't that seem strange? To solve this theoretically, you need dark energy, because there's repulsive force pushing from the center. Either that, or there's gravity at the boundary of the universe. We can't explain that right now. I think the mechanics, or the origins of the universe, are going to keep getting overturned.
Maybe space isn't that vast after all?
It might exist,